Good morning, students. Myself, Pradeep Kumar Vadha from Electronics and Communication Engineering Department, Ashoka Institute of Technology and Management. Today, we are going to discuss linear block codes, that is a topic from information theory encoding. First, introduction. Introduction. The purpose of error control coding is to enable the receiver to detect or even correct the errors by introducing some redundancies into the data to be transmitted. So, what is the main reason behind coding is we want to transmit some data. So, while receiving it, we can get errors in some bits or uh, burst of bits. Then we have to have a system to detect these kinds of errors that are produced in the channel. So for this, we use error control coding that will be discussed, and we will be discussing more about linear block codes. As the name suggests, linear block codes, a block of string is encoded, or you can say added some parity bits to a block of data or message uh, at a time, and this type of coding is called block code when we add several redundant bits at a time to a block of message or data. Then we have also have convolutional coding in which in spite of coding a whole block of data or message, we code a stream of bits one by one according to the input given to the convolutional encoder. Then we have a block diagram of what we call linear block coding. We have suppose message which is of k bits, that is k information bits. Total number of 2 to the power k distinct messages are possible with these k bits. Then we have in center encoder that will encode these k bits into n bits. Okay, so the n will always be greater than k because we are adding some bits to k to finally code these message bits, and the code word, that is C, will be of n bits, small n bits. And next is why these block codes are called linear block codes. So a code is linear if the modulo to some of the two code words is also a code word. That is, if we have two distinct code words and we just XOR them, then we get a code word that is also a valid code word. That is why we call these block codes as linear block codes. And we represent these block codes as n comma k block codes. So next we will discuss the important basics of block codes. That is, if we code k bits into n bits, then obviously n is greater than k. Uh, we added n minus k parity bits to it to get n code words, n bit code words, you can say. So the possible combinations of n, small n bits, we can get 2 to the power n possible code words or you can say the combinations of n bits will be to the power n, but we have only k bits at the input, that is the message. So if we find out the number of possible combinations for the information k bits, we have to the power k combination, which will be less than the codeword combinations that we can get with n bits. So there are possibilities of getting, you can say, the invalid code words, because only 2 to the power k code words will be valid from the combination of 2 to the power n possible code word value. Next, we will discuss what is generator matrix. Generator matrix is something we use to generate these code words, or you can say to code a particular message. And generator matrix is obviously of matrix form as shown in the figure. You can see G is G1, G2, G3 up to Gk, and if we expand G1, it will have G11, G12 up to G1n, and G2 will be expanded as G21, G22, G2n up to Gk12, Gkn. So there will be k rows and n columns in this generator matrix. And we use a simple formula for converting the message bit into n bits by C is equal to M into G, where C is the code word we will get after coding and M is the message bits, or you can say message which we want to code, and G is the generator matrix. So here we will apply matrix multiplication to find out the code words, and the code words will be denoted by C, and it can be written as C1, C2 up to Cn, and message is denoted by M, small m, and it can be written as M1, M2 up to Mk. So we can code block codes as systematic and non-systematic. We are discussing here only the systematic form. So as we have discussed, the message bits will be of k bits. Message will be of k bits, and the whole code word will be of n bits. So we have to add n minus k bits that are extra, that can be called as parity bits or redundant bits for checking the message to be received at the receiver end is in error or not. The rate or code efficiency of the code will be given by R is equal to K by N, where K is the number of message bits and N is the total number of bits after encoding. So G can be written as Ik and P, where Ik is the identity matrix of K cross N, K cross K, and P is the parity matrix. So C is equal to Mg, as we have already discussed earlier. There is an example. I'm giving an example for encoding that is considered as 7 comma 4. So as we discussed, linear block codes is represented as n comma k. We have n is equal to 7 and k is equal to 4. Therefore, if k is equal to 4, the message bits will be of 4 bits. The message will be of 4 bits, and data matrix will be of 4 cross 7. As we discussed, it will be of order k cross n. So k is 4 and n is 7. So the generator matrix will be of 4 cross 7, and this will be given in the question itself, and just we have to perform the matrix multiplication to get the code, and C is equal to M into G. We will do it and we will get C is equal to at last 0 1 0 1 1 1 0, and we use the message 1110. As you can see, the last four digits of this code word is the message itself, and first three bits are the parity bits that we have added. So another method for finding out the code words is by putting the message bits as M1, M2, M3, M4, since we have four message bits, and code words as C1, C2, C3, C4, C5, C6, and C7, as we have as the question in the question we have been given that n is equal to 7. Therefore, the code word will consist of 7 bits, and we will multiply these m1, m2, m3, m4 into g and find out the expression for c1, c2, c3, c4, as we can see in the lower part of this slide. C1 is equal to m1 plus m3 plus m4. These plus are just modulo to addition, or you can say XOR operations. These are not normal additions or binary additions. These are XOR operations, or you can say modulo to additions. Similarly, P2 is equal to M1 XOR M2 XOR M3. C3 is equal to M2 XOR M3 XOR M4. C4 is equal to M1. C5 is equal to M2. C6 is equal to M3, and C7 is equal to M4. And after putting the value of M1, M2, M3, M4 from the question given, m is equal to 1 1 1 0, we will get the output as 0 1 0 1 1 1 0. Next, for decoding purpose, we use the parity check matrix, as we have discussed. For generating a code word at the transmitter end, we use generator matrix. Similarly, for uh, decoding purpose, we will use the parity check matrix, and parity check matrix can be given as H is equal to I n minus k P transpose, where I n minus k is the entry matrix and P transpose is the transpose of P, which is the parity matrix, which we saw in previous slides. It is also used for finding the generator matrix. Some properties of H and G are discussed in the next points. Just that is, if we multiply H and G transpose, we will get 0. Or you can say, if you multiply a valid code word into H transpose, we will get also 0. So there is example, consider a generator matrix of 7 comma 4 linear block code. H is given as in minus k p transpose, and G is given as p I k. The corresponding parity check matrix is given as this. So we have just multiplied the G and H transpose, and we got 0. Then for detecting purpose, we use syndrome decoding, and syndrome basically is nothing but the received code vector that we receive at the receiver into H. We find out syndrome by just multiplying the received code vector with the transpose of parity check matrix S is equal to R into H transpose. Suppose we are sending a code word C, and from the channel it gets corrupted by some error. Then at the receiver we will get R is equal to C XOR E, and the error will occur Suppose we say the error occur at a single bit, then the error that is occurred will change the code word and the bits. So as we are using binary, the bits will be flipped. That is, if we have sent a particular bit as 1, it will become 0, and 0 will become 1. So the error vector can be defined as ei is equal to 1 for if r is not equal to c, and 0 if r is equal to c. These are some of the properties of syndrome. The syndrome depends only on the error pattern, as r is equal to c XOR e, and ch transpose is 0. By putting this, syndrome comes out to be e into h transpose. And all the error patterns, if I at least a code word has the same syndrome s. So we also consider a decoding problem here. Let c is equal to 0101110, as we have encoded this code word earlier in the example. And suppose we get at the receiver end the second bit is flipped from 1 to 0, r is equal to 0001110 to be the received vector. If we calculate syndrome s is equal to r into h transpose, we will find out that it comes out to be 010. As we can see, we have multiplied r into h transpose, uh, and this comes out to be 010. So we just have to match the which row corresponds to this 010. So as we can see, h transpose matrix second row, yet that is 010 is also 010, that is same as the syndrome that has come. So the row of h transpose, that is 010, is second row. Then we can say that the second bit is an error, and we can just find out the error vector by placing 1 at the second bit and remaining 0, and we can find out the code word that was transmitted by simply XORing r, that is the received code vector, and the error code vector, and we will find the code word. So that is all for now. Thank you.